Sir, areas of specialization, sir. Quantum computing, cryptography, algorithm design. Sir, education is, sir has a doctorate of, sir is research scholar at IIIT Delhi. Sir, integrated science education and research at Vishwa Bharati from August 2013 to May 2018. Sir has honors and awards. Sir has accepted into the IBM Quest Advocate Program. Sir is won second position in the International IBM Quantum Awards 2019 in the Teaching Emmy Quantum category. Sir awarded Inspiration Scholarship by the Department of Science and Technologies, India. Sir invited for so many workshops like IBM Quest Global Hackathon and IBM Quest Summer School and Young Quantum Computer and Query Complexity, Communication and Fourier Analysis of Boolean Function. Sir has many research like quantum algorithm for nonlinear of Boolean functions, and most Sir has done most research on the quantum computing. And Sir is specialized in Quist, MATLAB, Git. Sir is the a mentor in the challenge in the Quist Challenge India conducted in associate with IBM. And Sir has done Sir is one of the computing in Quist organized by Delhi. So it's my warm welcome to Sir. Sir, it's my honor to thank you, sir. Sir, please hand over the session, sir.
Okay. Thank you, ma'am. Hello, good morning, everyone. I hope I'm visible and I hope I'm clearly audible. If I'm lagging, please let me know about that. It's actually a great pleasure for me to have a session for you people. Okay, let me share my screen. Hope my screen is visible.
Your screen is visible, sir.
Great, thanks. So yeah, so I'll be doing two sessions so I'll be taking both the sessions of today, and on both the sessions we'll be discussing on how you can. So in the past 2-3 days, you would have got a basic idea on how quantum computing works and how quantum algorithms are developed and what are the existing quantum algorithms and stuff. So today we'll be giving a small session on how can we actually implement these algorithms. Like, right, theory is a part, but we need to practically implement it somewhere, right? Otherwise, it doesn't make any sense to just keep developing up the theory. So the first session will be talking I'll be showing you how to implement algorithms in Qiskit. Qiskit is basically a Python environment that is developed by IBM. So this session's agenda is initially. So I'll start by introducing what is called an IBM Q experience. IBM Q experience is basically a GUI-based web platform where you could actually do a lot of circuit composing and stuff. Then we'll go to Qiskit, which is the Python-based, which is a Python-based program, and we'll have a slide or two on Qiskit versus IBM Q experience, like what are their advantages and their disadvantages, and then we'll conclude with what we can do more with Qiskit and then resources. So this will be agenda for this session. Before we start, it would be great if you people. So since this is a hands-on, if you people could actually follow. It's like if you people could also code at the same time I'll be coding. So we'll not be needing anything, any special kind of installation. So whatever we'll be doing it online. So that should not you wouldn't be needing specialized softwares or packages as of now. Great. And please feel free to anytime you feel you are not getting something. And yeah, I'm always ready to answer your queries. Great. Right. So, okay. So, IBM Q experience is basically, like I said earlier, it's basically a website-based platform. So it was developed by IBM to give uh, uh, a and so that was why the name like IBM Q experience, experience of the quantum computers on for beginners basically. So you would be able to do a lot of stuff, but not like so you would be able to some small circuits, and you would be able to implement how each gate transforms the state of a qubit, which we'll be seeing in a minute. So in IBM Q experience, so we'll primarily be focusing on three stuffs today. One, I'll be showing you what are the available quantum computers, the actual quantum computers, not the simulators, computers that are available, which like any of us can use as of now. Then I'll be talking about some composer, where we'll actually be able to build a circuit and we'll be able to run it in a simulator or an actual quantum computer as per our need. And I'll talk a little bit on what is called an open QASM. Open QASM is a language, is basically it's a computer language that was developed initially for creating circuits, in the sense like actually for creating circuit diagrams for books. Later, that got adopted to coming up with creating and executing circuits in a quantum computer. All right. So let's head over. Right. Okay. So uh, so I'd like you to go to quantum-computing.ibm.com. Right. So this is the website, and probably when you first go, you'd be able to get a sign-in page, and you could sign in with Google or Git or LinkedIn or like any mail of your choice, and it shouldn't be hard. Once you sign into this, you will get a dashboard of this sort. Right. So in the first view, you can see that what you have is like a few circuits and results and stuff. So you have recent circuits that are implemented, you have pending result and latest and stuff. So, but first, I would like your attention to be on the right box over here. So here it says your backends. So these are basically all the available. So backends are basically quantum computers or simulators. They're called backends. Here you'll be able to see a lot of palettes, and each of these are the available backends on which you can implement a quantum circuit. Right. So you have like IBM Q Santiago, IBM Q Athens, IBM Q Valencia, and stuff. Now, if you click on any particular palette, you will be taken up to a pop-up screen where it gives you the name of the machine and the version, of course. It tells you whether it is in online or whether it is in maintenance, and the queue here tells how many jobs are there. So these are just single machines, right? So anyone in the world can access the machines. So they code up the program, they code up the circuit, and they send it to the machine. And you can the machine, of course, does one job at a time, and the other jobs get queued up. Right. So now there is this structure of a graph-like structure which is visible. So this is called the topology of this particular computer. So IBM Q Santiago has what we call a linear topology. Right. So we don't need to get into terms. So what do I mean by linear topology? So these circles basically denote qubits, right? And the connectivity or the double-sided arrows between the circles basically denote the connectivity between the qubits. So, okay, so what do you mean by connectivity between the qubits? So now if you see, the circles are colored basically, right? So these color gives you an idea on what the error rate of that particular qubit is. And by error rate, so what I mean is, say if I want the qubit state 1, then I apply an X gate and I try to measure it. So now what is the probability? So I perform this some say 1,000, so say 100,000 times, and I'll see how many times am I getting 1 and how many times am I getting 0. Right. Now, since these qubits are practical devices, I mean, so they are basically semiconductors in a sense. They also have something called decoherence, right? Any particular qubit can stay in any particular given state or a state produced only for some limited amount of time. We cannot, so as of now, we do not have the technology to have a qubit in any particular desired state for infinite amount of time. Right. So, and this, say if I want to create this state to say state 1, then I'll have to, so the decoherence time, I mean, the time in which it can stay as state 1 is in the order of like microseconds, basically. Right. So that's very less, but like that will be enough for us to perform all operations. So the circle, the color of this perimeter gives us the error rate. So you can see that here the qubit number 0, qubit number 1, qubit number 3 and 4 have like quite low error rates. However, qubit number 2 has a very high error rate. Right. Now, you see this double-headed arrows. Again, the colors of the double-headed arrows are the error rates, but like double-headed arrows themselves represent connectivity between the qubits. So by connectivity, what I mean is, so if I want to implement any particular circuit in a quantum computer, right? So what I do, I put in some gates and I send it to the quantum computer, right? But not all quantum computers can work with all gates. Say for instance, I hope you people are familiar with the X, Y, Z and H gates. These are some of the very basic single qubit gates. And I hope you are also familiar with the CX, a C0 gate. Right. So if I say create a circuit with all this X, Y, Z and C0 gates, and if I send my circuit to this IBM Q Santiago, what it does is it converts these gates to the gates which it can perform. Right. So down below, if you see, there is something called a basic gates. Right. So where you have like CX, that denotes C0, ID, that's an identity gate. You don't do anything there. U1 is U1, U2, U3 are three different types of gates, right? So whenever IBM Q Santiago gets a circuit, it converts the gates of the circuit to one of these gates, and then tries to implement that in your in the quantum in the machine, basically. So here, if you remember, C0 gate, C0 gate was a gate that acts between two qubits, right? So you have a control qubit and you have a target qubit. If the control qubit is set to 1, target qubit flips, otherwise nothing happens, right? So this is an interaction between two qubits, right? So this interaction is done only if there is connectivity between two qubits, right? So if I want to perform a C0 between 0 and 1 in this quantum computer, I can perform that. However, if I want to perform between 0 and 2, what I have to do is I have to switch the qubit 2 and 1, flip it, right, using a swap gate, and then perform a C0, then again swap them back. Right. So this connectivity gives me.
Hello, sir.
Yep. Yeah.
Sir, sorry for interruption.
Yep.
There
Sure.
is some questions in chat box, sir.
Oh. Okay. Sec. Oh. Right. Okay. Sorry. So someone asked me like how log in. Okay. Right. Let's see. So you just go to this quantum-computing.ibm.com, right? And say you could, if you already have a Gmail account logged in your computer, you just click the Google, or like so you can sign it with your Google, or if you want to do it with some email, you can sign in using your email, right? Just put your email and password, and yeah, you should be able to sign in, right? And Oh, okay, so you can go a little bit slower, so that's not a problem. Please, if possible, you can just unmute yourself and ask me the questions, or like suggest me things. So that should not be a problem. Right. Okay, great. So, yeah, so these connectivities tell us about if we can implement C naught between those
Sir,
qubits or
excuse
not.
me.
Yep. Yep.
Sir, while logging into the IBM experience, quantum experience, we have to register again while login
No, so if you
while
have
login to
already,
the Gmail.
right. So no,
Yeah,
so you
just I
just
clicked on the G.
so you just give your Gmail ID and
Yeah,
you just have to sign in basically,
yes, I
right?
signed
Either
in.
your
After
Gmail
that, it is
password.
asking some agreement,
So you just
something.
okay.
Just,
Just so you just so you just click on the sorry about this. So if it asks for agreement, so there'll be below there'll be an option where you can
yeah, yeah,
actually yeah
yeah,
yeah
accept
you
that.
accept
Yeah.
and go inside. Yeah, I think you should be able to go inside.
Then after that, it is asking for tell about yourself.
You can
Tell us
skip
a
that
little more
for
about
now.
yourself.
I think you can skip that for now. I think there should be a skip option.
No, no, sir. Actually,
Except not there. Okay. Oops. So you can just probably you can write down a few stuff, and that should okay. Let me do it. Right. So if it asks about something, you can actually fill up. So it will probably ask you a few stuff about these account details and stuff like what you would be interested in and things. Right. As of now, you can fill in details as you want, and later I think you can also change it as per your need. So probably it will ask something of this stuff. Right. So I hope that can be done.
yeah.
Right. Okay. Cool. Great. Great. Right. Back
Thank you.
to the up. Okay, cool. Sure. Right. So getting back here, so we were talking about the connectivity, right? So yes, so these connectivities between the qubits become very important, and the reason why it becomes very important is if we have any circuit and which consists of like any gates you want, those circuits can actually be decomposed in the sense like those circuits you can create exactly another circuit which can be implemented just by single qubit gates and CNOT gates. Right. So you just need a set of single qubit gates and CNOT gates, and you'll be able to implement any given circuit that you can come up with. Right. So CNOT gates form a very important. So CNOT gate is a very important gate actually in the all available gate set. Right. However, the problem is the error rate in CNOT gates is quite high. So it's so if you see so here the error range. So here you have like CNOT error rate. The range in itself is from 5 into 10 to the power minus 3 to 2 into 10 to the power minus 2. However, if you see the error rates for single qubits, you have like 10 to the power minus 4 to 10 to the power minus 3. So it's like the error in CNOT gate is twice as costly. So it's at least 10 times more than that of a single qubit gates. So that is the reason whenever people try to you try to reduce the number of CNOT gates as much as possible. We'll get into that in some time. Yeah. So now you have, okay. So down below you have the number of that this machine has. So it has 5 qubits, right? And since when is it online from? The maximum number of maximum shots. Okay, I'll come to what shots are in some time. Last, and it has a quantum volume of 32. I'll again, when we are actually implementing circuits, I'll tell you about what quantum volumes are. Basis gates. These are the gates which this particular quantum computer can implement. Right. So if I give say an X gate and a Y gate in a circuit, that will be converted into one of these gates, and then it will be implemented in the machine. And the maximum number of circuits that it can implement at any particular time is 75. So I can create a job of one circuit, send it to there, and it will still run. I can also create 75 completely different circuits and still make it send it there, and it will run everything and send it to me at once. Right. Okay, let me see if there are any questions. Great. Okay. So now, so if you hover over, so you will see there are 5 qubit machines, again 5 qubit machine. This again has, Athens has a linear topology, you can see. Again, now this is another, Valencia is another 5 qubit machine. However, it has what we call a T topology. It resembles the shape of a T, so it has a T topology, right? So here, if you see, this one particular qubit is connected to 3 different qubits. Right. So it can perform C naught with any of these three. Right. With just one gate, without doing any swap or without doing anything. Right. However, this is much denser. So even the graph looks much denser than the previous two machines, and the denser the topology is, the better we'll be having the connectivity in a quantum computer. Right. Great. Then you have a Vigo, which again has a T topology. Well, so all these are 5 qubits. Here you have something called Melbourne, IBM Q Melbourne. This has 15 qubits. Right. So this is the largest system that is available to all. The largest it was actually 16 qubits, so there was one qubit over here. However, it started malfunctioning, so they decommissioned that particular qubit. So it has 15 qubits, and this is what we call a ladder topology. Ladder, so just like you get up on a ladder. This is a ladder topology. And so here, say if we want to implement circuits of higher size, so this is a good machine. However, if you see, you'll find a lot of qubits with high error rate. So if you see 1, 2, 3, 4, 5, 6, 7 qubits at least, which have very high error rates. And similarly, if you see the connectivities, you'll find a lot of connectivities with a very high error rate. Right. So this is a problem that we are dealing with currently, where you have, as the number of qubits increase, as we are trying to build a quantum machine with more qubits, the error actually increases. Right. Error increases a lot. And right now, the research is, a lot of people are researching into how we could reduce this error. And yeah, that's a very active area of research. Right. So then you have another 5 qubit, and here you have something called IBM Q Monk. Right. So it's fascinating. It's a single qubit machine. Right. So you might be wondering, what can we even do with a single qubit machine? But however, this particular machine has, so in the earlier machines, what we do is we create a circuit using gates, and we send it over to the quantum machine, and the quantum machine implements it. However, in this particular machine, we are provided a complete access to the qubit. So what qubit, whenever a gate is implemented on a qubit, so if you see it physically, what happens is you have, so we have some waves, right? That a wave of some particular frequency is hit on the qubit, right? And depending on the gate, the frequency of the wave changes. Right. So on an so from an outside perspective from outside would be like we are sending it gates and some of they are implementing it, right? However, over here we ourselves can give any frequency we want, right? So we have the ability to actually send in any frequency we want for any amount of time we want, right? So that is the advantage of IBM QR Monk, and this is done by what is called a pulse, right? We have a separate package for this called Qiskit Pulse, and you can use Pulse, and you can do a variety of experiments on this basically, right? Because generally, say even so, if you want to measure it, so measurement is also done by sending a frequency. Generally, there are errors in measurement, and depending on how much time you send the wave, you can kind of reduce or increase the errors in stuff. Cool. And at last we have what is called the IBM Quasum simulator, right? So this is basically a simulator. This is not an actual quantum computer. Here, if you see the basis gates, it has a lot of gates in it, right? So since simulator, right? So it's just some matrix multiplication. So you can always put any gate you want, right? And it has 32 qubits. You can simulate up to 32 qubits. So this is an online simulator, right? And so whenever we try to implement an algorithm, we first check if the algorithm is right with the simulator, because simulator gives you exact results, in the sense like gives you results with zero error, right? And then if algorithm turns out to be right, then we implement in the actual machine, right? So these are all the quantum machines that are available to you, actual machines. And if you are interested, if you want to do, if you are doing research and if you want to do more research, you can also ask for like access to a few more machines. Yeah, and currently the biggest quantum computer that is available to, I mean, not to open, but like to people who are working in IBM is about 53 qubits, right? So it has a very big, its topology is a bit messy, right? It's a bit dense, but its topology is a bit messy. However, yeah, so 53 is the highest we were able to achieve with good fidelity, right? Okay, so now if you go to the left,
Sir,
okay,
excuse me.
yep, sure, sir.
These all are like a free. We can use it with free
Yeah,
first, or we have.
yeah. No, so all these machines are freely available. So like, so yeah, we'll even be implementing in one of these machines in some time. Yes, sir.
Oh, okay.
Right. Okay. So right. So now if you go to the left top, this hamburger menu, let's click on that. So you'll get a few options. So of course, dashboard. We are in the dashboard. Then under the tools, you'll have jobs, circuit composer, and quantum lab, right? So you go to jobs, that will give you all the jobs that you have submitted to this, and all the jobs that you have run in any particular quantum machine, right? And next, if you go to circuit composer, this will be more interesting, right? So if you get to circuit composer, so this is basically a place where you can actually construct a circuit, right? You construct a circuit, run it on some machine, and check out what the results will be, right? Okay. So first off, you can see that there are like three single lines, and a double line that is the composer. So each single line represents a quantum wire basically, and which means that there is a qubit over here. You have a Q0, you have a Q1, Q2. So you have 3 qubits, right? Say if I want just a single qubit, you hover over that Q2 or Q1, you can delete the qubit, right? If I want to add, there is a plus sign. You can you can okay, you can add there, or you can actually uh, okay. So I'll get to that first. So first, you see, say we have a single qubit, right, and the double line is what is called a classical bit. So whenever you have a qubit, you perform some quantum operations on that. You perform some gates, put on some gates and stuff, and you have to measure it. So if you don't measure it, you will not get any information out of the system, right? So you'll have to measure it so that you get some information from the quantum this thing. And whenever you measure, you always save it in a classical bit. So you measure it, you will get 1 bit of information per qubit, and you can save that in the classical bit, right? So let's first start. So whenever this qubit is, like when there is no gates, this qubit basically gives so this will be in a state 0. So if you see, right, so if you, these are all the available gates, right? You have a H gate, and this is called a NOT gate, X gate, right? This is a CX, this is a Toffoli, this is a swap gate, and all these, right? So let's, before we get into that, so in the gray buttons, you have a measurement button. So there'll be kind of a meter like symbol button. So you can just drag and drop it there, drop it on the qubit, right? So you'll have something like this. So the meter basically corresponds to measurement, right? So drag and drop it there, and let's run it, right? So for running it, on the right top, you'll be able to see there is something called run settings. You can click on that and go to backend, and you can select IBM Q Quasum simulator, right? So initially, let us do it in a simulator, then we'll get over and perform the same on an actual machine, right? So you perform it on an IBM Q Quasum simulator, and you try to run it, right? So you see a job that pops up, says like pending job. You have some job ID. You click on that, it goes to a new tab, right? So once the job gets over, you will get your result here, right? So okay, now that our status is completed, so this box will give you the measurement, and you can see in the bottom, so this is just a 0, right? Of course, we have a qubit, we have not done anything to the qubit at all, we have just measured it, so it will be in the 0 state, right? And this will give you a small idea on the time that it takes to actually implement a circuit, right? So if you see this timeline, right, here it says the transpiling has been done for in 800 milliseconds basically. Oh sorry, it's actually microseconds, 837 microseconds. So 837 micros. So transpiling is changing the given gate to the gates which the quantum computer can actually implement, right? So earlier, if you remember, we saw like any particular quantum. So this particular quantum machine can implement only these gates, right? So the other gates have to be converted to these gates, and that is done by what is called a transpiling, right? So there are like very powerful transpilers which are in the backend. It takes around 800 milliseconds, microseconds. Validating, it takes about 800. So validation, so it checks whether the circuit is right or if there is some error in the circuit, and it puts it in the queue, and it runs it, right? So it was my mistake, it's not microsecond, it's actually millisecond, right? So running takes like 2 milliseconds, right? So of course, and the total time taken is 4 seconds from the creation till the completion, right? And it gives you what backend you have done, and right. So okay, so coming to shorts, I'll tell you what shorts are. Short is basically the number of times I want this circuit to be implemented, right? So uh, so if I keep shorts to be 1024, uh, this circuit is implemented 1024 times. So it gets measured 1024 times, right, individually, and the aggregate result is given as this, right? So what is the need for shorts? So the use of shorts will be very evident in just our next circuit, or like in just one more circuit, right? uh, Now let's try to implement an X gate. So you see there is a circle with a plus, so that will be an X gate. You can just click and drop it here, right? and let's just again run it on Quasm simulator, and I hope I hope you people get what to expect, right? So you have a 0 qubit, you perform a NOT gate, right? You get a 1 qubit, right? So yeah, you get a 1 qubit, right? 100% 1 qubit. Cool. Right. Now, these are all, now very important gate is a H gate. Right, Hadamard gate is considered one of the important gates, and I hope you people were shown this. Hadamard gate basically creates an equal superposition of 0 and 1. Right, so it will create a state 0. So it will create a state 0 plus 1 by square root of 2. Right, when the input is 0. So I give a Hadamard gate. Right. Okay, just give me a sec. Right, and okay. Right, I put an X gate, I put a Hadamard gate, and I run it on Quasm simulator. Now you'll be able to see you. Okay. Right. So what we'll have is equal super. So you'll have equal probabilities of 0 and 1. Right, as evident from here. So you see, like you obtained 0 with 50%, 50.6%, 68%, and you obtained 1 with 49.31%. Right. So this kind of tells us that the Hadamard gate creates an equal superposition of 0 and 1. Right. And now you can see why the shorts are evident. So when you create an equal superposition of 0 and 1, when you measure it, so the state basically collapses to either 0 or 1. Right. So if I perform just one measurement, I would never be able to see if they are in equal superposition or not. Right. So I perform some, like say 100 or 1000 measurements, see that both the probabilities are equal. So now I know that the state which I measured was an equal superposition of 0 and 1. Right? Great. So this being on one hand, we can actually visualize what is actually happening. Right. Okay, give me a sec. Okay, let me put it up. So now if you drag this up a bit, you'll have sometimes you'll have a single box or you'll have two boxes, right? And these boxes will tell you what the measurement probabilities are, right? So this will basically tell you what the outcome will be, right? So again, here you can see that probability of the state 0 is 50% and probability of state 1 is 50%. Right, so this will give you measurement probabilities as bar graphs. Say if I add another qubit, so I can add, okay, oh, right, hold on, right, cool. So yeah, so this will give you measurement probabilities, right? Now you click on this drop down, you can select the other this thing. So you'll have something called a state vector, right? Now what is the difference between, so measurement probabilities basically gives you just the probabilities of obtaining these states, right? Probabilities of obtaining 0 and probabilities of obtaining 1. However, a state vector basically gives you a good idea on what the state is basically. So the color represents so I hope you people know that any particular single qubit quantum state can be given as 0 plus some e to the power I theta of one state, the whole by square root of 2. Right. So this 0 plus e to the power I theta, that theta is called the phase. That's called the relative phase between 0 and 1. Right. Now, as say if you put 0 equals pi, theta equals pi, then you will have 0 plus e to the I pi 1, which will be like 0 minus 1. Right. Or if you put theta is 0 or 2 pi, then you'll have 0 plus 1 state. Right. So in this case, so with respect to the angle of 0, so you can see that phase angle is given as pi of state 1. So which means that the state that we have is 0 minus 1 state, right, and not 0 plus 1 state, right? So the state vector gives you a more apt representation of what state you have just before measurement, right? And there'll be on the other box you'll have something called a Q sphere. If Q sphere is not visible, you can always go to view and you can press on Q sphere, right? You'll have a box that is coming up. And yeah, so another thing in state vector is that you will also get an a vector of the amplitudes, right? So in probability measurement in the measurement probabilities graph, you will get the probabilities. However, the state vector, you will get the amplitude vector, right? So these are amplitudes of these particular states. So here you can see this is nothing but 1 by square root of 2. So the amplitude of 0 is 1 by square root of 2, and amplitude of 1 is minus of 1 by square root of 2, right? And as for the colors of the face, you have a small legend that gives you the color, the face corresponding to each color, right? Now on this side, you will see a Q sphere, right? Okay, so Q sphere is nothing but it's just a general, it's another way to represent any particular qubit. So it's basically a sphere, right? And over here you can see a blob, a stick and a blob basically. So for every state, now the size of the blob tells you the probability of getting that state. So here we can see the size of the blob in both 0 and 1 are same, right? So so we will not be able to so just by looking at this, we'll not be able to get the exact probability, but you can get an idea on how the state looks like, right? So the blob size are relatively the same, so you'll get 50% of 0 and 50% of 1. And the color of the stick and the blob tells you the phase, exactly like the state vector. So state vector, the color told the phase of 0, phase between 0 and 1. And here also the color will tell you the phase between 0 and 1, right? Again, so there is a legend here. And yeah, so this is what a Q sphere does, right? On the composer, yeah, give me a sec. On the composer, you have a small disk at the rightmost part of the composer, right? Now this disk is what is called a phase disk or a phasor disk, right? It's called a phase disk. And if you hover over the disk, right, it'll tell you details on what the relative phase is and what the probability of 1 is. So the blue region tells me the probability of 1 and the gray region tells me the probability of 0. All right, so you can see you have like half the circle as blue and half the circle as gray. So it's like again 50% of getting 0 or 1. And you can see a small line that goes from center to the outer part of circle. That will tell you the phase, right? So if it's on the left, you have phase phi. If it's on the right, you have phase 0, right? But this is just another way of looking at the state. Right, great. So now, say if I want to add more qubits, right? So we go to this plus, click on the plus, right? And we get more qubits, right? Okay. And say if I want to apply another Hadamard over here, let's see what happens. Okay, and I measure it. So now you can, now you can see that earlier it was just 2 bars because there were only 2 possible states, but now you have 4 different bars, right? So it gives you like 4 possible states. And in the Q sphere, you can see that there are also like 2 vertical blobs, but there are also 2 horizontal blobs, right? So yeah, so how to read these blobs? It's exactly the same in any particular. Now we see the poles will contain the extremes, right? And in between the poles, you will contain what are the intermediate states, basically. So in the sense, like you have so 0 0, the state 0 0. You have the weight of the state 0 0. So weight is basically the number of ones present in the state. Weight of the state 0 0 is 0, right? And in this 0 1 and the 1 0 state, the weight is 1 because you have just one number of ones, and here you have two number of ones. So so this will be arranged according to the weight of each state. So if I give another uh, qubit, okay, another qubit over here, and say if I put another Hadamard, now you will be able to see Q sphere like this. Okay, just give me a sec. Okay, right. So you'll be able to see a Q sphere of this sort, right, where the top will be like weight 0, then you have three states with weight 1, then down you have three states with weight 2, and the bottom you have like one state with weight 3, right. So these are some visualizing aids, and these are some very basic ways on how you can actually implement a circuit, right. Okay, so say I hope you people are okay. So any questions till this point, anyone? Okay, in the chat. Okay, okay, please feel free to stop me in between. Right. So now that we have put the gates here, how do I delete these gates? So to delete these gates, click on the gate, right click on the gate, and press delete. Right, right click, press delete, and that should do. Right, or you click on the gate, press a backspace. Click on the gate, press a backspace, it goes off. All right. So now let's try to create what is called an entangled state. Right, a state which has two qubits and which has the state of the state will be of the form 0 0 plus 1 1 by square root of 2. I hope you people are familiar with the entangled states. All right. So the way how we create an entangled state is you apply a Hadamard gate and you perform a C0 gate. Right. So now you see, right now I think it's the right time to introduce you to what is called an inspect. So on the top, one of the tabs will be inspect. You click on that tab, right, and you can kind of enlarge this the visualization. So now you see, inspect will give you what the state is just after implementing this gate. Right. For instance, in this case, you have 0 0 qubits. Right. Just you implemented Hadamard on just the single first qubit. Right. Now, what will be the state of the qubit? It will be, you will have 0 0 and 0 1, both with equal probability. Right. And the phase of both will be the same. So you'll have 0 0 plus 0 1 will be the state just after this Hadamard gate. Right. Now I click on the next. Now you see, it will tell me the state after implementing a Hadamard and C0. So before implementing C0, you see that you have 0 0 and 0 1. However, just after implementing C0, you can see that 0 0 plus 1 1 is available. Right. So now we know that. So this is the state that we want, and what we can do is we can basically add in measurements, and maybe this time let's run it on a quantum machine. Let's see which quantum machine is relatively free. Right, so everything has a lot of jobs except for, say, let's go with IBM Q Athens, that has the least amount of jobs. Click on IBM Q Athens, and so in the same bar you'll be able to see the job limit on the right. Right, so this tells you the number of jobs you can submit simultaneously. So you cannot have more than 5 jobs in queue. So once it gets implemented, that's fine. Once you get the result, that is okay. But like you can have at most 5 jobs that are implemented at any particular time. Right. So okay, so my shots, let me put it to 1000. Right, and I'll run it on IBM Q Athens. Great. So however, this will take some time. You can yeah, since you have like about 20 jobs ahead of you, it will take some time. So by the time it gets completed, let's look over to the, let's get to the other one. So this is an entangled state, right? And how do we, okay, so great. So now, so this is how you basically create any particular small circuits in a composer, right? You just drag and drop gates and you measure it. You can run it on actual machine or you can run it on a simulator, and that will work for you, right? So next will be our open QASM, correct? So in the same tab as that of jobs, if you go to code, right, you will see something called a code editor, right? This particular code is called a QASM code, right? Like I previously said, this code was actually first built so that people can create circuit diagrams, right? Even some of the top books in quantum computing have circuit diagrams made by this code. However, IBM incorporated this, and now like slowly all companies are kind of incorporating this particular code to run the circuits basically. And so generally we don't use QASM codes, right? But just to give you an idea. So these are the initializations basically, sort of like the headers. So here it says you have like a quantum register, the name of Q, and I need 2 qubits in that, right? You want a classical register with again 2 classical bits. So to implement a gate, so say if I want to implement an X gate, you press the gate and you apply on which qubit you want to apply it on, right? And as you code, your circuit here also keeps getting changed, right? Say if I want to implement say a Z gate on Q1, so put this and you have this, right? And the measurement is of course, so this is like just like a reading, English basically. I mean, it's like a man's language, right? And if I want to say 5 qubits instead of 2, so I can just edit this to 5, right? I'll have 5 qubits. You'll be able to see the change in the composer, and you can perform whatever you want, right? Great. Okay, so this is it with open QASM, right? People don't generally use this much, right? So yeah, anyone having any questions at this point till now? Anything at all? Anything regarding gates or how to implement this stuff, or yep, anything? Okay. Okay, so assuming that we don't have any questions, uh, looks like this will take a lot of time. Uh, so now the next part is what? Okay, so now if you click on the hamburger menu again, the next is what is called a quantum lab, right? So this is basically you have a set of notebooks like Jupyter notebooks. I hope you people are familiar with Jupyter notebooks. If someone doesn't know what a Jupyter notebook is, then it's very simple. It's just a platform where you can implement your Python code in it, right? A Python code, and you can so you can of course run Python code in terminal also. However, running a Python code here will give you like real-time results, and visualization and stuff becomes much easier, right? So this will contain all the notebooks that you have. You can create a new notebook, right? In the meantime, it will take some time to open. In the meantime, let me explain you what these are. So these any of these will contain notebooks on these particular fields. Say for instance, if you get inside the chemistry, these will contain notebooks that will give you a glimpse on how to so this will give you a Qiskit code and a basic tutorial on how you can use Qiskit for chemistry, right? And similarly, you have general quantum algorithms. You have tutorials on how to create like so the basic circuits and what all can you do with circuits, on finance, on machine learning, and on optimization and stuff, right? So this was for the chemistry. Uh, So certainly, like in the chemistry, you can basically, one of the hard problems is to get the energy of any particular molecule or an atom, right? So this will give you a good idea on how to simulate the molecule in a quantum computer, and to get the energy level as close as to the actual energy level as possible, right? Okay, so now if you open a, so now I think your notebook should be opened by now, right? So in the first tab, this is just some basic imports, right? The first way, how you say, assume, let's assume this is not there. So the first way, how you uh, get into a Qiskit code. So now this is a place where we transition from the GUI based circuit creation to Qiskit based circuit creation, right? So before that, what actually is Qiskit? So it'll give you a brief. I'll give you a brief idea on what Qiskit is. Uh, Qiskit, like I said, is basically a Python framework, right? Where you can use Python to code quantum circuits and implement them on quantum simulators or quantum machines. Yeah, and Qiskit has four basic parts, or like four basic components, right? Uh, Qiskit has what is called a Terra, an Ignis, an Aqua, and Air, right? So Terra takes care of the very basic circuit creation and transpiling the circuit. Transpiling is like how you can change the given gates to the gate which the computers can implement, and how so Terra also deals with the connection between, like so it also deals with the connection of how, like, so it's the online cloud based implementation of circuits, right? uh, then you have Ignis, right? Ignis deals with the noise in the system. So, like I said, simulators give any results perfectly, right, without any errors. However, when you talk about real machines, like I said, have decoherence, and it cannot withstand, it cannot contain any particular state for a long time. So, with time, the what we call it. We call that particular process a state decay, right? All the higher energy states starts decaying to lower energy states, right? And so a lot of errors will be crept in. So Ignis helps to mitigate those errors, right? How we could so given the current configuration of the quantum computer, it will tell us how to mitigate those errors, and it will also help us to simulate those errors. Say if I know my computer's current configuration is this, my actual quantum computer's current configuration is this, then Ignis will let us simulate those errors in a simulator. Right. Then Aqua contains all the algorithms, all the chemistry algorithms, or finance, or even advanced computer science algorithms, like all the quantum algorithms, is basically. And it also contains small packages of very basic quantum algorithms, like Simon's or Does-Josa, or the Grover's algorithms and stuff. Right. Uh, Air deals with simulations, right? So Air package, so the Qiskit Air contains a lot of simulators, which we'll be seeing in some time. It contains what are called multiple simulators. In essence, you can simulate what the probabilities will be, right? You can a simulator which will give you the probabilities, simulator which will give you the state vector, or simulator which will give you the matrix of the circuit and stuff. So that is dealt with Qiskit Air, right? Okay, so now back to code. So first, we try to import all packages from Qiskit, right? We import all, right? And to run any particular cell, you press Control and Enter. The cell runs, right? And you want to create a new cell, you can you press a B to create a new cell below, or A to create a new cell above, right? uh, so first is always so we'll follow this pattern basically. So first let's see how we can create quantum registers, right? Because basically qubits are the basic information quantum informational units. So to create a quantum register, what we do is we assign Q, and you give the number of qubits that you want. Say initially I want just a single qubit, right? So uh, if I try to print Q, you'll see that Q is basically a quantum register, right? With one qubit in it, and it's named Q0, right? So this is quantum register is basically a quantum register class. So Q will basically be a quantum register. So a register is one or multiple qubits together. It's called a quantum register, right? So if I want a quantum register but with two qubits, I can just simply make it two, and I can name whatever. I can give whatever name I want. Say I want, say, register one. Uh, register one, right? So now you see, like, Q is basically a quantum register which contains two qubits and with the name register one, right? Okay, so by default it will be named Q0, right? So some Q0, Q1. Now uh, how, okay, so I have a qubit. Now the next thing that I need is I need to put this in a quantum circuit, right? So I create a circuit by this code, right? Circuit will be quantum circuit, and of course quantum circuits will contain qubits. So I put what are the qubits that I need to be inside the quantum circuit. So here I basically say oops yeah so here I say I need a quantum circuit, I need to create a quantum circuit that has Q as its qubit, right? Now I try to print this, you will get something of this form, right? This will, so this is basically a circuit. Of course there are no lines here. It's a circuit with two qubits in it. Now as we add gates, you will understand like why it's printed like this. So yes, now remember, if I want to measure a qubit, then I'll have to store it in some classical bit, right? And the way how I do this, so to do this I need some classical bits also, right? So I get a classical, uh, I make a classical register, right? I'm planning to measure both the qubits, so I'm giving both the two, I need two classical bits. So now my circuit, I'm making my circuit where I mean with Q as my quantum qubit and C as my classical bit, and I have this. So it says that like my class, I have two classical bits. Okay. So now once I have created circuit, let's see. Say I wanna add some gate. Say I wanna add an X gate, right? I wanna add an X gate to both the qubits of Q. How am I going to do that? So it's quite simple. So you put circuit dot, you know, on the circuit on which you want to implement the gate. You have circuit dot X is the code for X gate, and in the brackets you give the qubit numbers, right? You give Q0, and you have circuit dot X, you have Q1, right? Now let me try to print it. So here you see I have a qubit Q1 and qubit 0 and qubit 1, and I have X gates implemented on both of them, right? So so this is if we implement any particular gate. Say now I can implement, say you have Y gates, so which you can attach by circuit dot Y. Say let me put it on Q0, and I have Z gates. Uh, right. Say I have H gate. I have circuit dot H. on 0. Then say I have S gates, T gates, right? So everything is quite simple basically, right? Circuit dot the gate, and in the braces you give on what qubit you want it to attach, right? You print it, you get it, right? So X, X, Y is attached, Z is H and S, all these are, right? Now remember we said C naught is an important gate, right? So what is the code for putting a C naught in the circuit? Say I want my C naught to go from 0 qubit to 1 qubit. So I do this by this code. So Cx denotes C naught. So the first argument that it takes is the control qubit, right? And the second argument that it takes is the target qubit, right? So first one is the control qubit, second one is the target qubit, and implement it. Now we have a C naught here, right? So a better way to visualize these is you have the circuit object in itself has something called a draw function. So you have circuit draw. Uh, you get this. So this is drawn using matplotlib, right? So this gives a more elegant way of looking at the circuit. So you see, uh, so appending gates to the circuits are quite easy, right? Okay, great. So, well, we have done creating circuit, we have done adding gates, right? Okay, great. Now we need to measure the qubit, right? Of course, ultimately, at the end of all circuits, I want to measure it, and the measurement is done using this. You have circuit dot measure. You give the qubit which you want to measure, right? Comma, you give the classical bit where you want the measurement result to be stored, right? So you have circuit dot measure, Q0 is measured to C0, and you have circuit dot measure where Q1 is stored in C1, right? So now we have measurements, right? So this is how we actually come up with or we create any particular quantum circuit, right? Say now the advantage of using Qiskit can be shown now. Okay, so before going to that, so there are other ways of actually attaching a quantum gate to it, right? So well, this looks elegant and clean, right? But this doesn't give me a lot of support, in the sense, say if I want to append just a Y gate, right? Uh, so okay, this oops, this will do, right? I have appended a Y gate. This should do, right? But what if I want to append this Y gate, but not just Y gate? I want to append a controlled Y gate, right? So controlled Y gate is works exactly like a controlled NOT gate. However, instead of a NOT, you will have a Y. So you can have circ.cy, right, which is controlled Y. Okay. Oh, sorry. So of course you need to give a control and a target, right? So controlled on the first qubit, the Y gets implemented. So that basically means if the first qubit is 0, nothing happens to the second qubit. But if the first qubit is 1, Y gets implemented on the second qubit, right? But say if I have 3 qubits, right, and if I want to implement control, so control on the first 2, if I want to implement a Y here, I would not be able to do it just so another CCY doesn't help, right? So because there is no CCY object. So to overcome issues like this, uh, this Qiskit has a library called a circuit library, right? So can import, right? So from Qiskit.import and library has gates. These have gate objects, right? Not the gates themselves, but the gate object. So this will have something right, and it will have something called Y gate, right? We can use this in a better way. Okay, so I'll tell you how. Similarly, okay, we create a 3-bit quantum register, and my circuit is going a circuit then just queue. Right now I'm ignoring Germans. So now, say if I want to implement an X gate, but not just an X gate, but third qubit controlled on the first 2 qubits, right? So to give you, right. So on this qubit and this qubit, I want to implement uh, Q0 and Q implement an X. Done quite easily using the gate set from the library. So that is done as follows. What I do, I dot circuit dot end, right, and I give the gate, right. Uh, Gate is an object, and I give so I Q0, right, the qubits on which I need, and Q2, right, and X want a control version of Xgate, right? So Xgate dot control, right? And how many controls? I need 2 controls, right? So now if you implement, you that control on this qubit and this qubit, right? Target, I mean X is applied on. This will give you more control on 5 qubits, right? And I want to have on 4 qubits basically. So basically, you know, you can as much as you want. Very easy way of applying the. So very similarly, I can Y gate, uh, gate, right, or you can H gate, right. So you can put basically put any gate you want. So you have uh, X like we saw, Y gate, you have XS gate, you also have CX gate. So these are some of the very basic gates that you might have come across. Use any of these, and you just have the gate. You give like gate dot how many controls, and you give the qubits. Right. So whenever your circuit has a lot of controlling on the other qubits, always use sort of ending gates to the circuits. Right. However, if not much control, not controls are there, qubit, you can always this sort of taking. Right. So this should give you a very basic idea on how you would be able to circuit. Right. The next part, and what will be the last for this particular session, is I'll tell you how you can visualize these circuits. So, okay, uh, let's go back one. So circuit dot draw. Circuit dot draw will give you something of this form, but this is the only way you can visualize. Right. So there are like 2 more ways to visualize a circuit. Right. So you have draw. In draw, you give it a parameter. Say you give text. Right. So it will give text format. Right. Basically built in bad kind of. This will be visualized when we do not have like graphical this thing. So this will be helpful. You also have something LaTeX type. Will give you all in a white for colors, right? So okay, however, this is taking some time. So this is another way of visualizing, right? Okay, yeah. So you have code like this. Sorry, you have your circuit visualized like this. then the normal way will the MPL, so matplotlib, right? So that is what is given by default, right? So these are three ways of visualizing your circuit, right? So I hope at this point you people are like at least a bit familiar with how you can construct a quantum resistor with certain qubits, classical resistor with certain qubits, and you can also create a circuit, add a few gates in the circuit, right? And how could you measure it? How can you like, visualize the circuit, right? So starting from the next session, we'll see how you can implement these circuits in maybe a simulator or in an actual machine, right? And we'll also try to implement some very basic circuits along with so basic circuits of creating, say, a Bell state or GHZ state, or basic circuits on how you can kind of simulate a classical circuit in a quantum circuit, right? Of course, if we can implement and or and not gate in a quantum circuit, then you can of course implement any classical gate, right? Uh, and we'll also talk a little bit on implementing a few more of what are called Oracle-based algorithms, right? So, yeah, does anyone have any question at this point? Anything regarding whatever we talked from the start till at any point here?
Sir,
Yes, sir.
sir, by implementing these circuits, how what we can achieve, sir?
Okay, so whenever we try to come up with a circuit, so every circuit corresponds. So say we have a problem, right? For instance, let's take a very simple problem. Say you have a set of you have an array and you have some say 10 elements in array. So you have
Okay.
numbers 1 to 10 in an array, right? Now you want so the array could be ordered in any fashion, right? It's unordered.
Okay.
Now say if I want to choose the element 8, right?
Okay.
Classically, what would we be doing? So we see the first element, right? See if it's 8 or not, right? If it is 8, then okay. If not, then we check the second element, right? So we keep doing this, right?
Okay.
In the worst case, 8 could be in the last element in the
Yes.
array,
Yes. Yes.
right? So you have to basically traverse. In the worst case, you'll have to traverse all 10
Or else I can use
elements.
quicksort and I can. I mean.
Right. So that is another way of doing it, right?
Yeah. Yeah.
However, we can try and solve the same problem in quantum with square root of that speed up, right?
Okay.
So
Yeah. Yeah.
square root in this is if you need n time in
One by n
classically,
time. One by
yeah.
square
Here,
root of n time we can do this.
so actually it's just square root of n time,
Okay.
right? So you can do it in square root of n. So basically, if n is say 100, you can do it in 10, just 10. So now, how do we do this in a quantum circuit, right? So for that you need a quantum circuit,
So by using
right?
these circuits and we are going to pass our input to these circuits and via these circuits we are getting output. Is it?
Yeah, exactly.
In that scenario, if there is a huge use case, then automatically the circuit will be in complex, sir.
So it depends on. So there are also simple circuits which have a huge use case. There are also, of course, complex circuits which have a lot
For
of use
example,
case.
if I want to solve a finance problem statement, like for a credit card fraud detection, in that scenario,
Right.
I would like to detect the credit transaction, which is a fraudulent data or not. In that scenario, I would like to build a very huge circuit.
Yes, sir. So in those cases, so I hope you'll be dealing with a parts of machine learning there,
Yeah,
right?
I will be using
So
machine learning. It will be easy for me to do to handle these with why because there are a number of algorithms to handle imbalanced data sets. But in this, it is somewhat complex. Why? Because first we have to build the circuit. But if I didn't know any circuit concepts, I like these kind of circuits, then it will be one of the toughest task for me to handle these kind of problem statements.
right. So that is true, right? So just getting back to your question on the credit card. So you want to find frauds in credit card transaction. So there also, of course, the circuits will be a bit complex, right? It will not be very complex. It will be a bit complex. Now, if you are planning to use, so right now, as far as I know, so we have like a lot of machine learning algorithms doing that, right?
Yes.
So there, of course, we'll bring in like the quantum circuit kind of stuff, right? And I think my colleague is going to give a good introduction on like the quantum machine learning and how quantum circuits can be used in machine learning in the second half of today. Uh, so yes, sir. So initially, so if you question is like how can we come up with these circuits that like even now like people are not sure. So there is no algorithm to come up with these circuits,
Sir, can
right?
we pre-process the data by using these circuits? Sir, for example, if there are missing values or if there is any outliers in my data set. So in that scenario, in Python, I can handle these things by using data wrangling techniques like pandas. I'm having NumPy. So by using these techniques, I can pre-process my data according to the use case. But
Yes.
here via circuit, how can I pre-process? It is somewhat a
So
complex task.
right, that's a good question actually. So now processing or pre-processing a data is actually very very hard in a quantum circuit, right? So whenever we deal with such situations, we generally what we do is we go on a classical quantum interlock kind of stuff. So we pre-process some data classically, then we make that data into quantum, and then we run our quantum algorithms.
But
So
if
that
you
is how we generally, yes sir.
But if you go with the quantum, then automatically we are analyzing a situation. Superposition and entanglement are not being done by using these classical computers. Why? Because if there is a particular state, it must be either 0 or 1. It can't be same at
Yeah,
same time.
exactly,
So
exactly.
in that scenario, I'm going to avoid this quantum principle. How can I achieve final? How can I achieve this? I mean, how can I correlate that classical data to the non-classical? I mean, to this quantum machine.
So that is another wide area of research that is going on. So what is called a QRAM. So QRAM basically converts a classical data to a quantum data, right? So now, so it's so that is one of the very limiting areas of the quantum computing right now. So we are still not sure how. So we know how we can convert a classical data to quantum data, but how to do that efficiently? Till now, we don't actually have any very efficient algorithms, very efficient general algorithms, right? So that is actually, sir, is a very active research area that is going on right now.
Okay,
Yeah.
fine.
Yes.
Thank you, sir. Thank you
Sure.
for this opportunity.
Sure. So, yeah. Any questions? Anyone else?
Sir, can you provide the resources of learning these basic gates? For example, how to start? For example, if I don't know any kind of a gate, then there should be a start point, right, to do these things.
Right.
So can you suggest me some of the basic links to go through these?
Certainly, sir. Certainly. So, at the end of the next session, I'll give you a list of links which will actually help you, get a very good and a very elaborate introduction on whatever I'm talking. So,
Okay, the thing is, sir, finally I should solve some use case with respect to finance sector, sir. Not only finance, even though it might be any domain, I should solve that use case by using ML, using QML, quantum machine learning. I am familiar with ML, but I am not familiar with this quantum thing kind of
yes, sir.
algorithm.
Right. In the next session also, I personally will not be dealing with the quantum machine learning part. So in the next session, we'll be dealing more with some of the basic circuits and basic things that the computers basic
Yes, sir.
computer
Yes, sir.
questions. But the second half of the section, I think it starts from about 1 o'clock.
2:30.
Yeah,
Okay, fine.
1 or 1:30. I'm not sure. So I think 1:30, right? So the next two sessions will basically be completely on quantum machine learning. So you don't have to be worrying about that actually.
Yes, thank you, sir.
Sure. So let me stop sharing. Yep. If anyone has any questions.
This IBM dashboard is completely for free, right? I
Yeah,
think
yeah.
even if I can run n number of instances, for example, if I run multiple Jupyter files in this particular instance, they are not going to charge any kind of.
No, no, no. So there is absolutely no charge there. It's completely free actually.
And is there any kind of GPU? I mean, for example, if you go for Google Colab or any Paperspace, they are rendering a GPU or TPU. Or can we see these things in this Jupyter?
So basically GPU. So the way how So you can certainly run Qiskit on GPUs in the sense like, so the simulators basically, when you want to run the simulators, you can always run it on the GPUs. Frankly speaking, if you can install Qiskit in Google Colab, you can also basically run Qiskit in Google. But certainly, like if you are planning to run on actual quantum computers, then you don't have like any other platform, right? So you just have these. So there are other platforms, but they don't offer their quantum processing units for free. These are the available. Yeah.
Yes.
So yeah.
Yeah. Fine. Thank you.
Sure.
Sir, can you take any small example, and can you like any physical example, like chemistry, some electronic structure, or the type of small example? Can you take it, and can you please show me how to do it? Because I
Okay.
am
Okay, sir.
interested to do some quantum kind of stuff, like some electronic structures or something like that. Is
Okay.
it
Okay.
possible to do?
So I'm not. So I'll try my best to cover that in the next session, sir.
Okay, sir.
Because we have some stuff in the next session where we'll be dealing with a few problems, but I'm not sure if they are like very related with the electronics and stuff. But certainly I can introduce maybe say quantum Fourier transforms and stuff, which might be helpful actually.
Yeah, okay, sir. That's what at least like some quantum operators, how we can use it, and how to solve some type of problems, small problems.
Yes, sir. Yes, sir. That
Yeah, thank you.
yeah, well, yeah, sure, sure.
Sir,
Yes, sir.
this small last question.
Sure.
Sir, generally in yesterday's class, I have seen that quantum teleportation.
Yes, sir.
Right now, normal teleportation is also not is been done 100% up to 100% extent. Why? Because if there is an object, if you want to project that into teleportation, then automatically the structure of the object is going to be changing.
Yes, sir.
I mean, object is built up of molecules, right?
Right, sir.
So in that scenario, I'm going to lose that entire shape and dimension of the particular. So
Right, sir.
how can we achieve these things by using quantum, sir? I mean, we can't project a human being to transform some XYZ place, but we can transform a pen, or we can transform something. But the position, the dimension of the thing is been changing. For example, if there is a 3D, if I project that data, I mean, if I project that my mobile to some XYZ place, then automatically the dimension of the is been changing. Then it is been taking so much of time to pre-process that to come back to the same structure. So why should we go with teleportation with quantum
So
in that
certainly,
scenario?
right. So basically, if you see, say, let's take a very simple, say, let's take a pen, right? So certainly everything is made up of molecules, right? Now, classically, if you see, it will certainly take a lot of pre-processing to. So basically, the amount of energy, it takes classically for a pen to be teleported from one place to other. You can basically probably buy an air ticket for the pen and send it over to that place. But if you see in an intricate scale, all the molecules follow quantum mechanics, right? So you take any molecule, say it has atoms. So now these atoms have what are called their own states, right? And they are not classical states, quantum states, in the sense like they'll be in superposition and stuff, right? So certainly now using quantum mechanics, quantum mechanics also, like quantum computing also has access to superposition, it has access to entanglement. So using these, we can theoretically we can successfully teleport. So as of now, what is possible is we can successfully teleport information, right? And according to physics, any particular matter is basically information. So that basically means like we can successfully teleport any matter, but theoretically, right?
But you are saying that, sorry, sir, to interrupt.
Please,
But you are saying that, you are saying that we can transfer information. I mean, bits of data. I mean, qubits of data from one place to another. Then automatically the dimension of the data has been. For example, I'm sending an Excel file. It consists of 10 rows and 5 columns. So if I transform, then automatically the dimension of the sheet or the dimension of the data has been transformed to some XYZ data. Then in that scenario, I should again pre-process that data to the same data. Why? Because the end user didn't understand these data points. So again, it has been taking so much of time to pre-process. Then why should I go with teleportation instead of I can directly use classical data to transfer?
Right. So the classical. Okay. So so if you see, if you talk about pre-processing, that is not, so we'll be of course implementing quantum teleportation also. You would not be needing much of pre-processing, frankly speaking, right? If it's just data, if it's just some bits of data, right? Certainly, so if you have just bits of data, then certainly like it's easier to transfer the bits of data themselves. But in quantum teleportation, what we are interested in, not just the bits of data. Quantum teleportation, we assume that we have a classical channel, right? And we don't have a quantum channel, so we cannot transfer qubits, right? We cannot, yeah, transfer qubits. So you have some particular qubit state, right? So it is true that you said like if you want to teleport a classical data, so it's actually better to transfer it than to teleport it. Certainly that is true, right?
But if
But
there
in
is
quantum,
no quantum channel, then automatically, if any third party person comes and if he, like yesterday, sir gave me BB84 protocol, so there's a guy in middle, he might be corrupting my data. In that scenario,
exactly.
even though if I use teleportation, my data has been some noise or XYZ factor, due to some XYZ factors, then my data has been corrupted. So even
Certainly,
though if I use
yes.
quantum or if I go with classical, there is no security for my data. So how do
Huh, so
we fix?
that is very true. That is very true, sir. So security. So generally, when we try to come up with algorithms, we don't think it in terms of security, right? So there are a group of people like who deal only with security, right?
Yes.
And certainly, like BB84 is a very great example where you can. So of course, someone can kind of interrupt and put in errors in your data. However, like
Yes.
if you see BB84, we'll just be exchanging keys, right?
Yes.
And once we are certain that our this thing is secure, and BB84 ensures that, once we are sure about that, then like once we have keys, then certainly we can use quantum teleportation,
Okay.
right? Or certainly like we can, so we can basically encrypt and decrypt. So we are assuming that there is like passive eavesdropping. We don't assume that there is active. Of course, like someone can always come and block, cut off the cable in between, and that's an
Yeah.
active
Yeah.
eavesdropping. So we assume that there is no active eavesdropping. We assume that there's a passive eavesdropping. And right now even people are kind of trying to come up with algorithms where even active eavesdropping will not work.
Sir, have you practically done this teleportation in your day-to-day tasks? I mean,
So
have you any one MB of 2 bits of data? Have you practically done these things in your
Uh,
day-to-day task?
so practically in the sense, so teleportation happens at spatially separated places, right? So I personally have not done teleporting to different data. I mean, data to different places. However, we can kind of simulate teleport in the sense like, yeah, we can simulate teleportation in a quantum computer, right? So
Yes.
essentially you have two qubits, and you can entangle them, and you can create some other new qubit, and you can actually teleport that particular state to this qubit, right? So which we'll be seeing in next session, sir, actually.
Okay, fine. Thank you, sir.
Sure,
Thank you for
sure,
this opportunity.
sure, sure. Yes, sir. Yes, ma'am. Up. Yep, sure, ma'am, sure. Certainly, sure. Okay. Hello, ma'am. Yep, sure. Great. Okay. I hope most of you are back. Great. Okay. So, uh, in the first session, uh, we basically saw uh, how we could create circuits both in Qiskit, and we saw some detailed way on the website, so the GUI basically, right? So here in the second part, I would like to, so I would be going more in detail to implementing certain specific circuits and how we could execute them in real devices and how we could use simulators to get, to look at what the actual results are and stuff, right? Okay. So, okay. So again, like even for this session, it would be great if few people could actually follow me through the code, and that'll actually be helpful. Right. Nice. So okay. So let's start with creating, uh, uh, say, what we call a bell state. Right. So bell states are basically okay. Uh, Bell states are states of the form. Uh, uh, Probably you people know this. So bell states are states of the form this, right? Subject to, of course, you have a square root of 2 here, right? So basically, this bell state basically tells me that if you have one of your first qubit is measured to be 0, then second qubit is always 0, and the first qubit is measured 1 and the second qubit is always measured to be 1, right? uh, so this is a superposition, but it's a very intricate superposition. So this is what we call an entangled state, right? So this is called a maximally entangled state, but this is one of the entangled states, right? So let's create how to create this circuit in Qiskit. So we saw how to create this in the GUI setting. Let's see how to do this in this. So as usual, we import all possible libraries from Qiskit. Certainly, I need a quantum register, right? That has, of course, two states and classical register, so that I can measure and see what I'm getting. And let me create a circuit that has Q and C both, right? So we can see that this. Okay, so what's a very trivial way of coming up with this? So initially we have this state, right? So generally how we prepare a well state is we apply Hadamard in one of the qubits, right? So say I'm applying Hadamard in the first qubit, and I have of this sort, subject to, of course, let's ignore the normalization for now. So I'll have a qubit of this sort, right? So my qubits state, so initially it will be 0 0. I apply Hadamard then on the first qubit, so that I'll get a equal superposition in the first qubit and a 0 on the second qubit, and then I apply a C naught, right? So now C naught, so this is basically, okay, so let me write it as this. This is nothing but this plus this, right? So you have 0 0 plus 1 0, right? And if you remember, a C naught acts, puts an X or flips the second bit, right? Flips the target bit given the uh, uh, control bit is 1. So here control bit is 0, nothing happens here. Here the control bit is 1. So a flip happens on the second qubit only in this particular basis state. Nothing happens here, so it happens only in here. So this is how we create a bell state, right? So let's try to implement that. So first is Hadamard gate, certainly. So you have a H gate applied on Q0, right? So another thing which I actually forgot to say was, so you say if you have just one quantum resistor, right? You could, and you name that Q, you could write it as Q0, or you could also write it as just 0. So if you have just one quantum resistor, then 0, it basically implies that we are talking about the 0th qubit of the whatever quantum resistor is available, right? If you have more than one quantum resistors, then you will have to specify which qubit of which quantum resistor. But if there is just one, you can just give the index of the qubit. So we have circuit.h and we have circuit.cx, and cx goes from 0 being the control bit and 1 being the target bit. And certainly we need to measure. Okay, and same goes with the classical bit. The indexing also works with the classical register. So if you have one classical register, then you just need to give the index. That should suffice. Right. And circ.measure 1, 1. Right. So let's see how the circuit looks.
Sir, excuse me, can you please share your screen, sir?
Oh, sorry. Okay. Thanks a lot. I'm very sorry. Is it visible?
Yeah, yes, sir.
Yeah, great. Okay. So let me, sorry for the mistake. So let me go through this again. So say we want to create a bell state, right? And one of the bell state is of this form, right? So you have 0, 0 plus 1, 1 by square root of 2, right? And the way how we create this bell state is initially we start with the 0, 0 state, right? And you apply Hadamard on the first qubit, right? So you have 0 plus 1 on the first qubit and you have 0 on the second qubit, of course. Subject to the normalization. We are ignoring the normalization for the now. And so this is exactly the same as having 0, 0 plus 1, 0. Right. And then you apply a C naught given first qubit as a control and second qubit as the target. Right. So you will have 0, 0 plus 1, 1. So that's the state which we intend to get. Right. So, and how are we doing that? So we initially are setting up a quantum resistor with 2 qubits and a classical resistor with 2 qubits. Then you have a quantum circuit. Of course, we are constructing quantum circuit with Q and C. We apply Hadamard on the 0th qubit. Basically, like I said, like so, if you have just have a single resistor, so you just giving the index of the qubit suffices. So I am applying Hadamard on the 0th qubit and C naught from 0th qubit to first qubit. And I'm just giving circuit.measure. Right. So if we see this, so the circuit looks something like this. Right. So now I want to implement this. Right. I want to actually see how like if this works. Right. If this actually gives me. So what I'm going to do is I'm going to introduce you to something called a Quasum simulator. Right. So Quasum simulator is basically so the simulator basically creates a vector of vector. So it creates a vector for these 2 qubits, then implements this. So I hope you people know that each of these gates are nothing but just matrices, right? And whenever a gate is applied, so you apply a matrix on the vector, right? And every gate you keep a matrix, and the vector is your amplitude vector, right? And you take the norm squares of each of the element, you'll get the probabilities, right? So the Quasum simulator does exactly the same thing. It creates an input vector, and for people like who are not sure, so basically any state. So this state is given by the vector 0, 1 and 0, 1 and 0 transpose basically. So it's a column vector, and you have this is given by the vector 0, 1, again the column vector of course. And for any a, so this is basically you'll have the vector corresponding to a, say call it nt, and you make a tensor, right? You have a say en. Right. So basically, if you have a 2 qubit state, then you have the vector corresponding to a tensor producted with a vector corresponding to b. Right. So it will be a 4-dimensional vector, right? A 4-dimensional column vector. Right. So you have input as 0, 0. So you'll have the vector 1, 0, tensor 1, 0. Then you start applying matrices one after the other. Right. So this is how the Quasum simulator works. So so how do I implement in the Quasum simulator? So to implement it, so first I need to get the Quasum simulator, and we get the Quasum simulator. So let me call that the machine is air dot get backend Quasum simulate. Right. So now this machine is basically this machine indicates the Quasum simulator. So right. Okay. So it just gives the name. However, so this will contain all the details of the Quasum simulator. Right. Now I have circuits. So what I'm going to do is I'm going to make a quantum job, and that will be to execute. What am I going to execute? I'm going to execute circuit. Right. Uh, and backend will be the machine, so which is the Quasum simulator. And I hope you people remember the shots, right? Shot. I'm going to make 100 shots, and yeah, that's it. So that will give quantum job, right? So this Q job will basically be a dictionary, right, containing a lot of things like what was the time it was. Okay, so okay, so it'll be a job object. Okay, pardon. So it'll be a job object, right? This will basically be a dictionary that contains a uh, lot of information, right? But what I'm interested in is just the result, right? So my result, I can obtain my result in qjob dot result, right? Dot get counts. So this will give me the counts of each of the measurements, right? And I'm printing the result. Right. So here you see, we have 0, 0. We got 0, 0 for about 42 times and 1, 1 for about 58 times. But so we can see that the state is 0, 0 plus 1, 1. I mean, it could be 0, 0 minus 1, 1 also. But like from probability, we can see that like 0, 0 is obtained about as equally probable as 1, 1. Right. So you have any circuit. Now you create any circuit. You want to execute that circuit on a simulator. This is how you do it. So you basically get a machine. I mean, you get the backend from Air. Air, if you remember, Air is where we have all the simulators, right? And you execute the circuit in the backend with as many number of shots you want. You can go as much as you want, and you get the result, basically the counts by the job dot result dot get counts, right? And you print the result, right? Great. Say if I want to modify, say if I want to come up with a state of this form, it's more general than a Bell state. Say it's very similar to Bell state, uh, but of this form. So does anyone have any clue on how we could do this? So this is the state I'm interested in. I mean, so here you have two qubits where with states like 0, 0 and 1, 1. But here I have three qubits. I have 0, 0, 0, 1, 1, 1. So this is called GHZ state. Right. So could anyone have any ideas? But it's not very hard. Okay. Okay. So see, we are going to follow the same pattern as this, right? Except that we'll have another CX. The reason why we have is see, uh, we'll have the so basically the transformation that we are going to do is going to be very similar. We are just going to have Hadamard on the first, so that will give me something of this sort. And so this is basically this. And instead of applying just one C naught from 0th qubit to first qubit, I'm going to apply one C naught from 0th qubit and 0th qubit to second qubit, right? So that will basically give me 0, 0, 0. So the first, when I apply the first C naught, I'll get 0, 0, 0 plus 1, 1, 0, right? Then I apply the second C naught, I'll get this, right? So the only change that I need is to add another C naught from 0 to 2, right? Okay, so I need to have 3 this, and I need to change the measurement. Right. So I need 3 qubits now. So 3 classical registers just in case I need to measure. So this is the circuit. This is how the circuit looks like. And if you implement this, so we get 0, 0, 0 and 1, 1 with equal probability. So the reason why these so GHZ states and Bell states are very important is because they are used very extensively in error corrections. Right? Do you remember when we talked about the real devices? We talked about decoherence, right? And we said decoherence had effects on. I mean, so decoherence caused errors, right? So to reduce those errors, we use states of GHZ and GHZ state and Bell states basically, right? So that will so there are protocols which use this to reduce errors, right? But we'll not get into those protocols. So great. So this is I want to I implement. Say if I want just the counts, I implement it this way, right? Say if I'm not interested in the counts, right? So any questions till this point? I don't have any questions at all. Okay. Now, say if I'm not interested in the counts, rather I'm interested in the amplitude of the state, right? But counts will just give me the probability of getting something, right? Amplitudes will give me the phase information also. So if I'm interested in amplitudes of the state, then we use a simulator called state vector simulator. So instead of a quantum simulator, I have I use what is called a state vector simulator. And state vector simulator doesn't take shots. And here we don't have get counts, rather we have state vector. Right. Okay, so let's implement this. So here you see, this will be an basically a vector of size 8, right? And this vector is basically for any qubit, you see, if you want to represent any qubit, you need a vector of size 2. So if you want to represent 2 qubits, you need a vector of size 4 because you have a tensor product. So for any to represent any qubit of size n, you will need 2 to the power n sized vector, right? So so we have 3 qubits in our circuit, and we get a size. So this will represent the state vector. But if you see here, we just have 1 here, so it just says 0, 0, 0, right? Or everything else is 0, or just the first element is 1, right? 1 plus 0 j. That's basically 1. That is because of the fact that we have done a measurement here, right? Say if we run this again, so we'd get a different vector, right? See, right. So you see, you have a 1 at this point, right? So that's due to the measurement. So whenever we are dealing with state vectors, we need the complete vector. So we actually ignore the measurement. So we do not measure, right? So now it will give me the vector of my 3 qubits, the state of my qubits after these 3 gates are applied on. So now you'll see, you have like this is 1 by square root of 2, 0.7071. So you have 1 by square root of 2 at 0, 0, 0, 1 by square root of 2 at 1, 1, 1. Right. Okay, so this is how we get the state vector. So what my resultant vector will be. Say if I'm still not interested in vectors, right? Say if I'm interested in what the matrix of this looks like, right? So that can be obtained using what is called that's called a unitary simulator, right? So you have a unitary simulator, you have get unitary, right? So we just run it, and so of course this is an 8 cross 8 matrix, right? So it doesn't make sense just to look at this like this. But if we can extract and make a complete 8 cross 8 matrix, so you will see that this is the matrix which these 3 gates combinedly give me. Right. So if you want, you can get the probabilities, or if you actually want the state vector, you can get the state vector, or if you want the unitary, you can get the unitary. So these three are the simulators that are available in air, and this is like, of course, open. And the thing is, like, these simulations are run in your local computer. It's not run online actually, right? So in our case, we are using an online platform, so it runs online. However, when you are running it in an Anaconda, or like when you're running it in a local computer, the simulations happen locally, right? Okay, so this talks about the simulator, right? Say, but what if I want to run this on a real device, right? Say I want to run it on, say, let's see, say some machine, which machine, say I want to run it on IBM Q Athens, right? So first we need to check that the number of qubits are lesser than what is provided by the backend. So certainly we have 5 qubits in the backend, so we need only 3 qubits. Great. So in order to implement it on backend, so you need to get something called, so you need to link your local computer to your account, right? So that can be done by this. So you have, so you, so each account is given something called, so if you press on this icon, go to my account, you'll be having what is called a token, right? Qiskit. So you have a token here, it's called an API token, right? You can view it, right? It's a long token, you can copy it, and you can actually uh, use that to save here, right? Paste it here, right? uh, right, and I already have a token here, so let me overwrite it. Right. So this basically saves your token. So basically, then whenever you implement any particular circuit here, that will be linked to your account. Right. So I have this. Okay. Uh, now if I load account. Right. Okay. Now my account, and my account details are, I'm in IBM Hub, and it's an open group, right? So like everyone gets to get, so everyone who has an account is put into IBM Hub, and they are in the open group, right? Now now I need to get my machine, right? So machine is okay. So first, we have something called a provider, right? Just like the air package here, we have something called a provider, which provides us with all the required machines, basically. So it gives us information on what the machine, the available machines, and what the configurations of the machines are and stuff. So right, so I get the provider, and now I take my machine. Machine is provider dot we need IBM Q Athens, right? Great. So now we have a machine that's IBM Q Athens. Now if I try to implement, now okay, I can, now we do everything exactly the same, right? Now I have a backend, I have shorts equal to 1000, right? And here it will be shorts. Yeah. Another thing that I should probably mention is, whenever you are talking about the real machine, right? Whenever we want to real machine, you only get the probability vector. So you only get the probabilities. You don't actually get the state vector or unitary, right? Because in an actual machine, you run it and you measure it, right? So once you measure it, you only get the counts, right? Vector, these are only for the simulators. So to implement again, right? Okay. Sorry, not get counts. And so most of the times, sorry, did anyone ask something? Okay, so most of the times what happens is we can see that the queues are quite long, right? So just so we know where we are in the queue, we import something called job monitor, tools dot monitor. We import job monitor. I mean, you could use this, you might not use this, but it's always good to use this, right? And as soon as you job, you put job monitor on the queue job, right? So this will keep telling you which position, which queue you are in. So, okay, certainly now my machine, I've got the IBM queue Athens, and let's try running it. Right. So since you have a job monitor, it will show you the real status, current status of the job. So now you see like my job is queued like in the 37th position. So as time goes on, it will keep going down. And once it gets over, the rest of the code gets implemented. Right. And if you see, if you go to your dashboard and refresh it, you'll be able to see one circuit in the pending results session. Right. So this is the circuit that you actually submitted right now. And it also gives you the queue position and estimated completion. Now, since we have like a lot of jobs, estimated position is 37. So yeah, so it's expected to run in an hour, which is of course quite a lot. But yeah, now since there is a challenge that is currently going on in IBM, so a lot of people are using the machine. Otherwise, generally machines are a bit free, right? Great. So this is how I would implement in an actual machine, right? Now the problem is, like I said previously, in an actual machine, I might not actually get an equal superposition. So in this case, in the earlier case, we saw when you are implementing in a simulator, we were getting like kind of very close to equal 50 probability, 50%, 0.5 probability of getting 000 and 0.5 probability of getting 111. However, we cannot expect that in here. So let's see. If we remember, there was one. Wait. Oh, okay. Sorry. So there was one circuit, if you remember, that we implemented in our actual backend. So let's see if. Okay. Oops. Sorry. Just give me one sec. So that. Okay. Yeah. So in this circuit, what we actually implemented was, I think we, great. So yeah, so what we implemented was a bell stick preparation, right? So this is the original circuit. And since this particular backend cannot handle H gate, transformed it into a U2 gate, right, with some parameters. So the transfer is H based. So you have a H and this is a bell stick expected to get 50% of 00 and 50% of 11. However, you see that, okay, so we have around 50% of 0. However, we just have 45% of 11, right? So this is because of decoherence, right? Because of decoherence, one kind of decays to 0. So the first qubit 1 decayed to 0 like about 3% time, and the second qubit 1 decayed to 0 about 1.7% time. So you see, we get some errors. Now this is a very simple circuit, right? Implementing so this okay, so this circuit just has two gates, and just for two gates, you see we can there are some errors creeping up, right? So as the circuit size grows larger and as we use more number of qubits, we'll see that there will be a high error rate, right? And of course, like till now, we know how to mitigate this error, but we do not know how to completely remove this error off. So, and like a lot of research is going on in this stuff. So this is the difference between implementing something on a simulator and implementing something on an actual quantum machine, right? Simulator, it was around 50%, 50%, right? And recently there is a lot of people, a lot of research that is going on, coming up with new algorithms that can work in these kind of quantum machines, where errors uh, are taken into account, and the algorithm still performs good despite having those errors. Right, and these computers are called, these algorithms are called NISQ algorithms. So near-term intermediate scale quantum algorithms, basically that's NISQ. And yeah, so it's a very active area of research currently. Right. So going back to our this thing, as you can see that our Q has gone down, and let me stop it right here. Right. Great. So this is how we actually implement on an actual machine, right? And in fact, you can come up, you can write any circuit, and you can actually implement this on the actual machine.
Sir,
So
we handle situations before in histogram we have showed decoherence. So how we handle?
actually, so we don't have. So generally, what we do is we take the majority vote, right? Whenever so we see that 000 and 001 are the majority, so we assume that okay, so that is what the state was, right? But generally, like we so there is, so like I said, so we can mitigate the error. So this was run in IBM Q Athens, and so depending on its configuration, they have something called T1 and T2 times, that which are kind of like a decay times, which determine how fast decoherence happens. And depending on that, there are certain algorithms which help mitigate the error. Right.
So can we claim these outliers? I mean, can we claim these decoherence data as an outlier data?
Exactly, exactly. So it does have an outlier data. Frank, true.
Yeah.
So yeah, so but most of the much of decoherence work is being done by, I mean, increase the decoherence. I mean, in the sense like to increase the coherence time. A lot of work is going into physics and electronics, basically, because whatever quantum computers is all like circuits, and they use what are called Josephson junctions, and they use diodes and transistors. Like this is, yeah, we as of now we do not use an actual atom or an actual electron. What we use are what are called Josephson junctions, and we use transistors, basically.
I think we should.
Transistor
I
capacitors.
think we should reduce the coherence, right, sir? We should not increase this coherence. Why? Because coherence is nothing but corrupted data. If the corrupted
Uh,
data range is increasing, then automatically our data pre-processing or wrangling technique time is also increasing. In that
Correct. Actually,
scenario,
sir, it's the opposite. So coherence is like how good can the state be? Right. So if I make a state as one, how much time can the state be in one? That's called the coherence time.
I'm
Right.
talking about decoherence.
Decoherence, of course, sir. So we should try to increase the coherence time so that decoherence happens after a long time.
Okay, fine. Yeah, yeah,
Right. Yes, sir. So that's the thing.
yeah. Thank you.
So yes. So yes. So anyone has any questions? So at this point, like you should be able to, kind of create a circuit and be able to run it in a simulator or an actual machine. I hope uh, everyone is okay with that, or like any questions you can put forth. Okay, okay. Assuming there are no questions, let me go ahead. So, uh, getting back to this, so we basically created circuits and worked around with the circuits. We executed things in real devices and simulators. Okay. Um, we also ran Bell states and CHS state, but I also told you that we'll be running a classical. Yes, ma'am. Okay, sorry. Uh, yes, how to handle decoherent situations? I think we just talked about that. So mostly it's the physicists who are actually dealing with that, and they are trying to create states which are more coherent. However, like we can also get to know the current configuration of the system and kind of predict, kind of. So we cannot predict exactly, but kind of predict how much error could be possible and we can actually reverse it. So that's what we are currently doing. Yeah. So, yep. Anyone has any questions? Great. Okay. So then we'll jump into how we can come up with a quantum circuit to implement and, or, and not gates. Right. Okay. So let's start with not gate. So this is quite simple. Right. So what I want is, say I have a circuit. Right. I give it an input and I want the not of the input. Right. Now, I hope you people remember that quantum circuits have to be reversible, right? And certainly not gate is reversible, so it's quite easy, right? So, say if I have Q as quantum resistor, I have my circuit. In fact, so there is another, say if I have to make, okay, so there is another way of coming up with a quantum, creating a quantum circuit with some desired number of qubits. So you just type in circuit is quantum circuit and you just give the number of qubits that you want. Right. So if you have just one register, this is one register. I mean, I could also have like 4, 5 qubits, as many qubits that I want, but one register. Then certainly just giving the number of qubits should suffice. And right. So this will basically this is a not circuit, right? So I give it some input, I apply an X, so that's a not gate. So 0, if 0 is given, you get a 1, 1 is given, you get a 0. So this is quite evident and trivial, right? Now let's do an OR gate, right? Now this is a bit non-trivial, right? So what we need, now you see that OR gate is not a reversible gate, right? Given output, I cannot know what the input is, right? However, uh, I can make it reversible if I also have the information of the input, right? So if I am given an input and say if I'm given an input, I can get an output. But if I have some information about the input, then and an output, I can still make it reversible, right? So generally, this is how we create the OR gate. So uh, say I have, say for instance, so of course we know OR gate, be it 0 0 or 0 1 or oh, sorry 0 0 maps to 0 and 0 1 1 0 and 1 1 maps to 1, right? So okay, so now I want to create a quantum circuit where uh, my input is there, but so basically my inputs stay the same, but I also get the OR as an output, right? Because if input is lost, I'll not be able to get back. I'll not be able to make the circuit reversible, right? So what I do is this. So the first 2 qubits will be the input, right? So can someone think of a very plausible circuit? Right. 0 0 maps to 0, right? 0 1 1 0 and 1 1 maps to 1, right? What could be a good candidate for uh, right for an OR, right? So certainly, like, what one thing I can do is now if you remember C naught gate, right? What a C naught gate does on an input A comma B, where A is a target, sorry, A is a control qubit and B is the target qubit, is if you write this mathematically, A remains the same, however B remains B plus A. I mean, it's an XOR. Let me write it XOR A. Right. So A remains the same, but this gives me B XOR A. So let's see if this works. So you have a 0 0, still gives me a 0 0. Great. If you have 0 1, I'll still get a 0, 1. But if I have a 1, 0 or 1, 1, that gives me a 1. Right. So I can have circuit.cx from 0 to 2. Right. Let me draw. Right. Okay. So in the meantime, let me also, so to give a real-time idea, uh, hmm, I'll use Quasar simulator, and let me try to keep the shots to be say 10. Okay. Oops. Process 10. Let me print the result. Great. Okay. So what I have is, say, let me prepare the input. Say I have. So let me call A is something, and B. Say let me call A is this thing and this. If A 0. Right. So without this thing, so this will basically okay. Just give me 1 sec. Oh, right. Yeah. Of course, I need to measure. So another easy way to measure is basically to write circuit dot measure all. So this will measure all qubits, right? Uh, and one thing you should keep in mind is whenever you perform a measurement, right? So I hope you people are familiar with the big endian, small endian form of notation, right? So here, the topmost qubit is the least significant qubit, right? So the topmost qubit gets the rightmost result, right? Say, and if I make it 1, 0, so you see the topmost qubit gets an X, and the rightmost qubit becomes 1. So topmost qubit is the rightmost. The measuring topmost qubit will give me the rightmost bit, right? So if you wanna say make the topmost qubit the most significant bit, certainly you can reverse bits. Okay, this, okay, forget about this. So certainly you can, I mean, measure in a reverse fashion, right? You can measure say I to 2 minus I, right? And I need classical bits. So yeah, so you just measure in a reverse fashion, and you'll get the topmost qubit as the frontmost bit, right? Great. So let's go with the reversed measurement strategy, right? Okay, cool. So now certainly we can see that I prepare 1, 0. The state I'm measuring is 1, 0. So this will basically prepare my input. Now what I do is I perform circuit.cx on 0, 1. Right, let's see. So if I put a 0, 0, my third qubit is output, right? Third qubit is the OR qubit. So if I get a 0, 0, okay, I need a 0, I got a 0. Now if I put a 0, 1, well, I'm not getting a 1 here, okay? So for 0, 1, I'm not getting anything, right? For, let's see, for 1, 0, okay, give me a sec. Oh, sorry, you have 0 to 2, right? 2 is my output. So for 1, 0, you see I'm getting the output right. 1, 0 or is 1, 0. And for again 1, 1, of course, I'll be getting my output right. So we need to accommodate for 1, 0. Sorry, 0, 1. Right. So what I can do is, so I can say, now we'll be using the circuit, the circuit library, which will help us the control, appending the control bits. So what I do, I say append, I control on 2 qubits. My qubits are going to be q1, q0, and q2, and my control state. So I see that, like, if my qubit is in 0, 1, then I certainly want my output bit to change, right? And the order over here, so I hope you remember how we appended an X gate. So the last qubit is the target qubit, the first two are the control qubits. However, this the rightmost bit which we give in the control state is the which what we want as the control state for the leftmost what we give here. So okay, once we print it, we'll see. Okay. Oh, okay. Pardon me. Yeah. Now let's see. Well, let me give us 0, 1. Right. You see, now we have a 0, 1, and still you get a 1. So now you see, I gave a control state as 0, 1. Right. So which means you have a control. If this is a 0 and a 1, you implement an XOR. So you implement a NOT gate. Right. So you see, the first 0 is implemented on this qubit, right, and the 1 is implemented on this qubit, right. Say if I have, say, more, say if I want 1 0 1 1 0, and say if I have like 3 4 and 5. So basically the mapping will be the last 0 will be implemented on the third qubit, right. So I control my third qubit to be 0, then I control my fourth qubit to be 1, right, and I control my fifth qubit again to be 1, first qubit to be 1, and zeroth qubit to be 0, right. So it's like it's the reverse of the ordering of the qubits. Control qubits is reversed here. So that's something which I wanted to say, right. Great. So now let's see. Say I give 0 0, I get a 0 here, right. I give 0 1, you get the right state. 1 1, you still get the right state, and 1 0, you still get the right output. So basically this forms, this particular 2 lines of code form the basically simulates the classical OR circuit, right. Now I would suggest you people to come up with an AND circuit, right. Of course it's going to be 2 lines of code, and try coming up with an AND circuit, right. That'll be so now, so that'll be very easy, so you people can do it on your own. Now you have a NOT, you have an OR, you have an AND simulated in a quantum computer. So certainly, like, they are universal gates. Even AND and NOT in itself, they themselves are universal gates. So you can basically implement any classical circuit in a quantum circuit. However, the problem is you have an overhead, right. So classically you give 2 inputs and you get 1 output. Since it's not possible here because it has to be reversible, we keep the inputs and we have an output, right. We keep the inputs and we have an output. So for every gate we use some constant many qubits, right. So even though you can simulate classical circuits quantumly, it becomes a huge overhead, right. So that is the reason even multiplying 2 3-digit number, which takes like in order of like microseconds in a classical chip, takes so recently they showed that about it takes about 70 seconds just to multiply 2 3 qubit sorry 2 3-digit numbers, right. So that is why now people are advocating for not a complete, so quantum computers are completely, not going to completely push off classical computers and throw them off. Certainly we'll be needing classical computers, and we will classical computers are efficient in a lot of arithmetic sense. However, we'll be using like quantum machines like the GPUs, so we use it only for certain hard tasks, right? Okay, great. So yeah, any questions till this point? Next, we'll be jumping into say simulating quantum teleportation. But before we do that, any questions, anyone? Any questions regarding anything? Are there questions in the chat? Oops. Okay. Okay. Sorry, like I didn't zoom it in. Yeah. I can make these notebooks available if needed. So that should not be a problem, I suppose. No more questions? Okay. So then let's get into simulating quantum teleportation. Oops. Great. So if you people remember, let me just show you the circuit. So if you people remember, the circuit for quantum teleportation looked something of this form, right? So the first two qubits are with Alice and third qubit is with Bob. So basically the first the qubit, one qubit with Alice and one qubit with Bob are entangled, right? We create an entanglement using this. And Alice performs some operation and then she transfers two classical bits to Bob, right? And based on those two classical bits, Bob does something on his qubit, right? And Bob gets exactly the same qubit which Alice was having, right? So the complete circuit looks something like this, right? So let's try to do it, right? Say let's call A the quantum resistor that Alice has. She has two quantum, two qubits basically. Bob has one quantum resistor, certainly, and of course some classical registers will be needed because Alice will be measuring her qubit. Let's call this as my quantum circuit, which will have A, B, and a C, right? So when you have more than a single register, so this is how you initialize a quantum circuit, right? So you first give all the quantum registers, then you give the classical registers, right? So if you have more classical registers, you can just add comma and you can keep writing it more, right? Great. Okay, so now okay, let me call it by the name A. So this A and B, this is just for the visualization purpose, nothing else. So as usual, let's draw them. Okay, so now I have these. Now what I know is one qubit of Bob and one qubit of Alice are entangled, right? Otherwise teleportation will not work. So teleportation works based on the fact that Alice has some qubit which she has no idea what the state of the qubit is, and she wants to send that qubit to Bob, right? Now she cannot measure it because she has just one qubit. If she measures it, she collapses and the information is lost. Now she shares. Now the thing is, like, she doesn't even have a quantum channel. All she has is access to classical channel. So what she performs is but the resource that she has is entanglement. So she has a qubit that is entangled with that of Bob, right? So now our target is to send that unknown qubit state to Bob using just a classical channel and entanglement, right? So now let's first create entanglement pair, right? We create okay, and mod on Alice's 1 qubit and CX on Bob's 0. Okay, so this will this dot barrier is something that is just for visualization purposes. This is just a barrier so that the gates do not get mingled. Right. So now if you see the state of these two qubits is 0, 0 plus 1, 1. Right. If you want to make sure, you can always do this. L dot, I want to measure, okay, Alice's first qubit to 0, 0 and C1. Right. And I just yeah, let me put what the backend is. Right. Right. I keep the shots to be default. That is 1000. Like basically, it's 1024, and I get the number of shot number. So you see, right. So now we know that it is entangled. So you have just the state 0, 0 and 1, 1 and with equal probability. So this qubit and A1 and the qubit B0 are entangled. Great. Okay. Now let me create some state in A0. Right. So what I'm going to do is what I'm going to do is probably let's create a so let's just rapidly put a few gates in, right? Say dot x on 0, l dot s on a 0, and say l dot h on a 0. So this is some state which we even do not know what it will turn out to be, right? Okay, so we have created some particular state in A0. Now I want to teleport that. So the state in A0 should go to state in B0, right? So, okay. So if you remember, all Alice had to do was she had to make a C naught from A0 to A1. Okay, so let me try to bring in the picture. So she has to make a C naught from A0 to A1 and she has to apply a Hadamard. Right. So this is called measuring in Bell basis. Right. I'm not sure if you people have come across measuring in different bases, but once this gets over, like let me explain that to you. So let's do that. So you have tel dot cx that goes from a0 to a1 and on a0, right? Great. So now we have done this, right? Now what Alice has to, okay, so Alice has done two gates and she has to measure, right? Okay, let Alice measure it as this, right? Now depending on the measurement, you see, depending on the measurement that Alice makes, right? So Alice measures and gets her qubit. So the Q0 is stored in CRZ and here Q1 is stored in CRX. And controlled on these, Bob has to perform certain operations, right? So, right. So Alice, right? So she measures, great, and here. And so how do we, so okay, so now this is something again new to us, controlling, so performing some operation controlled on a classical bit, right? So what I know currently is my C1 contains A1 and C0 contains A0, right? uh, so how do we control some operation on a classical bit, right? So we knew how to do that on a quantum bit, but so on a classical bit we perform it like this. We put an X on whatever, so the operation that whatever we want to do. Okay, so we actually want to do it in Bob dot see if, right? So that it's like saying if the classical, so you perform this, given that classically my register, which is going to be C in this case, so my register C equals uh, okay, so now, so you see classical register here is 2 bits, right? So it can assume value 0, 1, 2 or 3, right? Now what I wanna, so if you see my Bob applies an X, right? Given that my uh, 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 second, so basically this corresponds to my, given that Alice's second bit is condition on Alice's second bit, right? So there are two ways so either there are two ways of doing this. Either you could do this, so this will just be 2, right? And I'll see if, oops, C is 1. So what do I mean by 2 and 1? So if I measure this, the top is going to be the least significant bit, this is going to be the most significant bit. Now if my most significant bit is 1, then I apply an X here, and if my least significant bit is 1, I apply a Z, right? So if my most significant bit is 1 and the other one is 0, so I have a 1 and a 0, right? And if my least significant bit is 1 and this is 0, we'll have like 0, 1, that's 1, right? And okay, right, but that is not all, right? What if we have 3 there? Like what if most significant and the least significant bit both becomes 1 and 1? So we perform this. So I would do this. uh, if it's if the classical bit is 3, I perform both, right? Okay, great. So now I claim that whatever we have in the Bob's qubit will be exactly the same as what was there, what was the state created in A0, right? Well, theoretically we can show, but practically how do I actually know that it is actually the state? Well, so you remember circuits, quantum circuits are reversible, right? So if I have a mechanism, if I have a circuit that goes from 0 to some particular state psi, then I can use the transpose of that circuit to go from psi to 0, right? So 0 to psi, you have a circuit, and you can use the transpose of that circuit to go from psi to 0. So what I'm planning, what I'll do is we used XSH. So this is going to be my circuit which created A0, right? I'm going to use a transpose of this and apply it here. Now if I'm getting all zeros, then I know that my teleportation is correct. If I get something different, then I know that teleportation is wrong, right? Okay, so let's apply that. So so if you remember or if you know, so if I have a circuit that has A, B, C, right, and I apply a transpose, then that is exactly the same as C transpose, B transpose, and A transpose, right? So this is very similar to yeah, so transpose is basically so this comes very simply from the matrix theory, right? So you have A into B, the whole transpose is B transpose A transpose, right? So in this case, I'm going to do, so we have X, S, and H. So transpose it. We'll have H transpose, which is H. S transpose, so that's a dagger. So here we don't transpose, we do use a dagger because we are dealing with complex these things. So H dagger will be H. Then we'll have H dagger applied, S dagger applied, and X dagger. H dagger is H, X dagger is X. So we apply H, S dagger, and X. Right. Let's see. So we apply H on Bob 0 qubit. We apply S dagger on Bob's 0 qubit, and we apply X on Bob's 0 qubit. I mean, why are we not applying H dagger and X dagger? Because H dagger equals H, X dagger equals X. Right, so they are their own daggers. Great. Okay, so now, okay, now what I need. So, okay, so let me create one more this thing so that we can measure Bob's qubit. Right. Date. Okay. Tell dot measure B0 into C10. Right. Okay. Let's see. Oh, okay. Sorry. Great. Now, if you see, the single qubit that is alone is that single bit is the measurement of the Bob's output, and this is that of Alice's output. Now, I'm not worried about Alice, but Bob, you see, every time Bob has a 0, right? Now, even if I increase the number of shots, say if I increase the number of shots to 8,000, my results of Bob's qubit are still going to be 0. So that basically means that the state that was teleported here was exactly the right state. Right. So the teleport that the state that got teleported was the right state, that the state that was actually prepared in A0. Right. So this gives me a way to check it. Right. Now we ran it on a backend. Right. Sorry, we ran it on a simulator. Now, if you try to run this on an actual machine, you'll not be seeing 0 always because of errors. You'll also be seeing some ones over here. Right. So that way we know that the state teleported was mostly, so for most of the time it was the exact state, but not always. Right. So yes, so this is the very basic teleportation protocol. And so essentially, if you see, here we are simulating. So if you are running it in actual backend, that is again like, well, you have say 2 qubits here, you are passing the information of this qubit to this qubit, essentially, right? So that's like a very small scale teleportation. And as of recently, the longest teleportation that has taken place is between a satellite and Earth. So China actually built a satellite which could, so, and they made some entangled qubits, kept some on Earth. So the entangled qubits, so one qubit they sent it to satellite, one qubit they kept it on Earth. So they created many such pairs. They sent the satellite to the space, and they were actually able to communicate, so teleport information from satellite to the Earth successfully. But like, so the according for the errors, apart from the errors, so the success rate was about 6%, right? But still, it is something. So that is the longest distance teleportation that has happened in practice. Before that, there was a lab in QTech, lab named QTech, which did a teleportation across about 250 kilometers. So now, what is this? What will this teleportation be helpful to? This, so there is a complete branch of research which talks about using teleportation for something called quantum internet, right? Yeah, so you have certain entanglement, entangled particles in your say local machine. So information can be sent just if you have classical bits. I mean classical channel. You can send the quantum information basically through the entanglement. So yeah, quantum internet is the most that benefits from quantum teleportation. Right. So yeah, any questions for anyone from this protocol, or like implementing the protocol, or like why or how we did this stuff? Anyone? And feel free to ask questions. Yeah. Okay. So if there are no questions, I'll introduce you to a last concept called something called an oracle. So oracle preparation. Okay, so what is an oracle? I believe that you people in the previous talks heard a lot about oracles, right? And in most of the talks, I suppose you would have heard that oracles are uh, oracles are something which you give the input, and they give you some particular functional value. So you give it x and it gives you some fx, and you don't know what the f is. Um and for most of the problems, oracles are already given to you in hand, right? You don't have to prepare the oracles. uh, but say in a real life scenario, it is generally the case that we have to prepare the oracles, or if you are giving oracle to someone, so you have to prepare an oracle, right? So how do we do that? So that is another very important area of research on the preparation of oracle. So as of now, we do not know any efficient way to prepare an oracle, right? So all any oracle, general oracle, random oracle preparation takes exponential time, or exponential gates essentially, right? So let's try to do something quite easy here. Say if I have a function of the form fx equals say 1 0 0 0 oh, 0. Oh, let's do something more simple. Say if I have one and a one here, right? Where this basically is f of 0, so this is going to be f of 0, right? And uh, this is going to be f of 1, or rather probably I should put it this way, 0 1, right? And this is f of 1 0, and yeah, that's going to be f of 1, right? Say if this is my function is defined this way, right? Now I need to create an oracle for this, right? So how do I do that? Well, so oracles are in such so an oracle is made in such a way that you give an input, right? You give an input x and some bit b, right? And you pass it through the oracle. What you get is you get an x comes out as x, but b comes out as b plus f of x, or actually it's not plus, it's b xor f of x, right? So any quantum circuit that can take an input of this form and give an output of this form is an oracle, right? Now to create an oracle for this, so certainly we are sure we need to oracle acts on 2 qubits, right? Okay, so uh, oracle, let's we have quantum circuit with 2 qubits, right? Okay, great. Now what I want to do is I want to get this implemented, right? So what is a very naive way of doing it? A very naive way of doing it is the oracle sees the input, right? Of course oracle has access to x. It sees x. If x is 1 0, right, then it flips the b bit, or if x is 1 1, it flips the b bit, right? So more trivially, uh, it will be like oracle dot append xgate, which flips basically, and control on 2, my control state is going to be first we have 1 0, and the qubit is what do we have? So 1 0 2, right? Because I want my 0th qubit in the state 1 and 1 qubit in the state 0. So because you have 1 0, and you flip the second bit, right? And so that will account for this, and for oops Yeah, for this one, so you can my control state just has to be 1 1. Right. Now let's see. Great. So okay. Index. Oh, all right. Just right. Okay, so this is the thing. So it sees that it sees if the first qubit is 1 and the second qubit is 0. Okay, I flip it. If the first qubit is 1 and second qubit is 1, I again flip it. Right. So I can like say if I have like any function of n bits will be like exponentially long, and I can keep adding gates like that. But that's again like we use exponentially many this thing, right? So in this case, you see we try to find some inputs that have common output. So this is what we call as blocks. So we try to find blocks of input assignments such that they kind of have all the say all the assignments in that block have the same output. Okay, so for instance, an example might be helpful. What I'm going to do is, you see, I see the first bit, right? And if the first bit is 1, my function is 1, right? So my complete function depends only on the first bit, right? So rather than doing this, what I'm going to do is Oracle il.cx, right? Depending on the first bit, it's my 0th bit, I flip this. So this will have the same effect as how these two were implemented, right? So when we try to create an oracle, this is how. So there are like certain algorithms which try to group this effectively. They use the CNF form of a function and try to group, try to find blocks of inputs which have blocks of inputs and input variable assignments that have the same functional value, and they try to implement that, right? Uh, but like even those algorithms are exponential in time. But so this is barring, assuming that we have like access to exponential gates and we don't have problem with exponential time. This is exactly how we create an oracle. Right, now once we create an oracle, we use it in any particular. So now say for instance, let's see if our function turns out to be right. Let me borrow some code from here. Right, so I have an oracle, right? What I got to do is okay, 3 it goes to command SI, right? uh, okay, now my wait, oh sorry, this is great. So you give input 0 0, you get the output as 0, right? uh, you give the input as oracle.x on 0, x on 1. So you give input as 1 0, you get a 1, right? Because 1 0 we needed a 1. 1 1 we get a 1 in the output, right? And we have 0 1, we have a 0 in the output, right? So now it's again b XOR of f of x, right? Now if I flip the b, if I put b equals 1, if b equal to 0, then I'll be getting fx exactly. If b equal to 1, then I'll be getting fx bars essentially, right? So this is how we generally create an oracle. So for bigger functions, we try grouping and stuff, but this is the ultimate way of creating an oracle. So whenever I have a function that needs to be turned into an oracle so that I can uh, uh, give it to the problem, So I can create an oracle, and in a sense I can even, right, so basically I created an oracle. I can put up, make this a function that returns this circuit, right? Diff or, right, right, and right. So now if I am kind of creating some circuit, say with some 5 qubits that does something something something, but say if I want to append the oracle, what I do is circ dot append the oracle, right, and I give the qubits on which I want it to get appended. So say I want to append it on 12012, then basically yeah, okay, let me do circuit.raw. Right, so 012, so my oracle gets appended in 012 qubits, right? Or like if I want to append in say 032, gets appended in 032, right? So now I can use this as a black box. I don't have to worry about this anymore. For any function I have to create oracle just once, and that is why we are not very much worried about the exponential time it takes, right? Okay, so I hope you people are familiar with the Doyes-Josa algorithms and Simon's algorithms, which needs oracles. uh, I would advise you to give that a shoot. Try to come up with an oracle. Try to implement the algorithms in Qiskit. Right. Great. Now, next, let's talk a little bit on the difference between the Qiskit and IBM-Q and what their individual advantages are. So certainly Qiskit is coding friendly, and creating large circuits are fairly easy. You can put in loops inside and all this becomes very easy. It provides access to a wide range of generic algorithms package. So even the Doyes-Josa algorithm, Simon's algorithm, Grover's algorithm, any chemistry algorithm, so you can actually implement them directly by, they have packages for that. Creating noise in the real backend. So you can use Ignis to simulate the noise of the real backends, and you can execute multiple circuits at once. So, right. On the other hand, IBM Q experience is more beginner friendly. The drag dot circuit makes it much easier for beginners to use, or in fact, like anyone, even if someone is if someone is interested in running just smaller circuits, they might find it easier to just drag drop and work on it rather than sitting and writing the Python code for that. And it allows for inspecting the state. So for someone who is starting with quantum, who tries to get a gist of how the circuits evolve the states, the inspect function in IBM Q experience is very helpful. And both of them provide very excellent ways of visualizing the state of circuits, and they allow for, of course, simulator and non-simulator backend accesses. You can run it on real machine or on a simulator, and it's a great way. So running programs and creating circuits and implementing them will give you a great intuition on how the quantum computing works actually. And frankly, so I can, from my personal experience, I can say that I've been working in this for about 3.5 years for now. And the way how implementing circuits transforms how you think it's a large actually. So the more you implement, you get to know what the actual problems in your algorithms are, and you can actually uh, learn a great deal of intuition on quantum computing and algorithms, right? So what more can you do with Qiskit? So like it said previously, you also have a pulse level access programming where you can set the frequency of a photon that you want to hit on the qubit. It contains a wide range of generic cross-domain algorithms, like those algorithms for chemistry, optimization, finance, and stuff. I'd leave you a link where you can check out those notebooks. It also allows for it allows you to get the configuration of the backends, right? So you have an actual machine, you can get the configuration T1 T2 times, and from there you can get the decoherence times, the errors of the qubits, errors in the connectivity, and we can use this as an input for your research on error reduction and stuff, right? So if you try to come up with an algorithm which performs better error reduction, you can use these configurations and check how good your algorithm performs. And Qiskit is Python based, and so Python has enormously a lot of other modules also, so it's very easily integrated with Qiskit. In the next two sessions, my friend will be talking on how you would use PyTorch and Qiskit together for solving certain machine learning problems. And it's an open source framework, and the network is Qiskit network is quite huge. A lot of people from IBM and from non-IBM are working, and anyone have like literally anyone who can open up an account has access to all the actual machines and the simulators. And anyone can actually, if you think that something is lacking in Qiskit, you can always contribute it via GitHub actually, right? So as for the resources, so these will be the resources. I'll probably share the slide with you, so you people can take this. So YouTube series for anyone starting with the Qiskit, YouTube series should be quite good. They have a small series called Coding with Qiskit. Qiskit textbook has enormously a lot of stuff that you can learn from the basic, right? And you also have Qiskit tutorials that, like I said, like contains multiple tutorials on like multiple subjects. And we also have a community tutorials which are developed just by the community, right? And of course, documentation and Slack are always there, which will help you question this thing. Great. Yeah, now it's your turn to try implementing certain algorithms and find out how to implement things better, or get some joy working on some algorithms, right? Yep. There ends my presentation. Thank you very much. So yeah, I can take questions if anyone has any questions. Let me see anything in the chat box. Great. Yeah. Any questions, anyone? Or like even does anyone have any suggestions? Even that would be helpful to me. Okay, so let me stop sharing my screen. Right. If there are, yes, ma'am. Okay, certainly if you people would like to interact with me anytime in the future, like I'll leave my contact details. You can always, yeah. Sure, madam. Certainly, ma'am. Oh, thank you very much. Thank you, ma'am. So the pleasure is mine. Actually, it was a great. It was actually very great session. Teach you people on how to work on Qiskit and stuff. Thank you.